Okay, we're going to take a minute to talk about orthonormal and orthogonal matrices. Orthogonal is defined as a matrix whose inverse, -1, is equal to its transpose. So that's a pretty easy law. I mean, if you got A, B, C, G, then its inverse, it's, A of -1 is equal to 1 over the determinant of A, B, C, D is equal to A transpose, which would be equal to, excuse me, this would not be A, B, C, D. It would be D negative B negative C A. So that's the A inverse is equal to A transpose, which would be A C B D, which would be the transpose. So if this is true for any given matrix, then it is considered orthogonal. So pretty quick deal there. It's pretty easy proof. For orthonormal, orthonormal. This is a little bit different. The conditions that have to be met for it are the A inverse is equal to A transpose, just like before, but the determinant of A has to also equal 1. So the process for determining if a matrix is orthonormal is basically to take the determinant and then find the inverse and the transpose, because you need the determinant in order to find the transpose. So we're going to use actual numbers here for this one because it's kind of a big one. So 1 over square root of 2, negative 1 square root of 2, 1 over square root of 2, 1 over square root of 2, square root of 2. So in order to get the determinant of A, that's this matrix A, this will equal just the product of the two crosses here. So we'll end up with 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2 times negative 1 over square root of 2. Just like that. So right there is these, and then right there is these, which is actually equal to 1. So cool, we've got that condition marked and set. Now, moving on to the next part, A transpose is going to equal 1 square root of 2, negative 1 over square root of 2, and then 1 over square root of 2, 1 over square root of 2. So basically you just flip along this diagonal to get the transpose. So we've got that transpose. Now to take A inverse, A negative 1 is equal to 1 over the determinant of what would normally be, just switch these two, you take the negative transpose basically of the opposite other diagonal of the normal transpose, and then you switch the signs on these. So we're going to take 1 over square root of 2, 1 over square root of 2, so that's not going to change, but actually these two values have flipped. And then we're going to take 1 over square root of 2 negative, and then we're going to multiply it by negative and get a positive. And then we're going to end up with 1 over square root of 2 negative down there. So the determinant is actually equal to just 1, so we end up with A transpose is equal to 1 over square root of 2, 1 over square root of 2 with the negative 1 over square root of 2 down here. And lo and behold, our inverse is also the same value. So these two are equal. So this condition is met also. So this matrix, A, is in fact orthonormal. So, good stuff.